welcome to my lecture today. I decided to pre-record this video because my laptop actually crashed initially, and I've just got a new one. So I want to, uh, apologize and, for any inconvenience that I've actually caused everyone. So give me 1 second. I'm going to share my screen now. Okay, so initially my laptop actually get crashed, and that is the reason why I'm doing this pre-recording. Welcome everyone to my lecture today. Uh, the title is actually Quantiles and Best Prediction. Okay, today we basically going to learn how what is the essence of quantiles, in statistical theory, and what can we actually call the best prediction. Of course, that is going to be in focus today. Okay, so we're going to start with quantiles. Okay, before I'm going to start with quantile first. Now, looking at the quantiles, if X is a random variable, okay, X is a random variable, and if we have a Q, and that very Q is actually, we call it the quantile of X, okay, or the distribution of X. So it's actually any number X, such that the probability of a random variable X less or equal to, a realized value is greater or equal to Q, and the probability of S greater or equal to X is greater or equal to, 1 minus Q. Okay, so, some of you may be wondering, what do we actually, mean by that? So, quantile actually defines a particular part of a data set. Okay, it determines how many values in a distribution are above or below a certain limit. Okay, so if you want to talk about, the the application of quantile in real life practical situation, you basically, by quantile, the quantile actually determines how many values in a distribution are above or below a certain limit. Okay, you want to know how many values, that are below or that are above a certain limit. If that is what you're looking for, automatically you'll be actually looking for quantile. Okay, now you remember we actually work with continuous probability distribution. So for instance, if a continuous probability distribution, you know, actually have a distribution function S, F, we've done distribution function the other time. So if a continuous, random variable, having a distribution function, okay, do you know we can actually equate the CDF, the distribution function, equal to Q, just like what you have here. Okay, so before you can actually figure out quantiles, you need to, the distribution function of the particular random variable must exist. And you know what? If S is a discrete, on the other hand, okay, having a distribution function, an uppercase F, okay, Then Q is basically gonna lie between f of y and f of x, situation where y is less than x. So I just wanted to take note of that. Okay, so now I'm gonna walk you through, for instance, visiting a particular distribution. How do we figure out the distribution function? Because you know why? Uh, Before you can actually compute, the quantile distribution function must actually exist. I'm gonna say that again. Before you can calculate, or before you can compute quantile the distribution function of that particular random variable x, must exist. Now, if you take a look at the example I'm actually citing now, you basically going to see uh, is that of a binomial distribution, with n. If you take a look at this now, it means you have the sample size equal to 3 and p basically equal to half. Okay, just take a look at what we have now. Okay, so that is we're focusing on binomial distribution, but you know what, before we're going to go into the binomial distribution, I think I need to also tell you, practically speaking, what we actually mean by what is the application of quantile. I told you the other time that the quantile actually determines how many values in a distribution they are above or below a certain limit. Okay, now I'm gonna give you an example. Now if I want to guarantee, okay, if I want to guarantee that 95%, okay, of my customers, okay, receive their orders within 24 hours. Maybe I'm a supplier, maybe I sell products, and if I actually want to guarantee that 95% of my customers receive their orders, okay, within 24 hours, okay, so how much inventory do I need to keep on hand? Okay, so if I actually anticipate, or if I want to guarantee that 95% of my customers receive their orders within 24 hours, okay, now how much inventory do I need to keep on hand? Okay, so definitely, quantile function is actually being used to figure that out. Okay, I just wanted to understand the practical aspect of that. So why the quantile, getting quantile is actually, symbolic. Okay, so, you know, if we have, if you have this, if a random variable is actually followed by binomial distribution, of course, what your the support of x, what support of x is probably going to be, right? It's going to be 0, 1, 2, okay, and 3. I think you remember that, right? The support of x is basically going to be that. And you know what, you are tossing a coin like 3 times, okay, because an example of this is a coin, because the p equal to 1/2, you got two sides in a coin, right? And the probability of any side showing up is basically going to be 1/2, right? Okay, so when you toss a coin 3 times, you remember I actually walk you through the tree diagram the other time. If you basically want to figure out what the sample space is basically going to be. So I'm gonna write out the sample space now. Okay, so take a look at this now. You're basically gonna have head, right? And you're gonna have head, tail. Then you're gonna have head. Then you're gonna have tail. Then you're gonna have head, right? You're gonna have tail. You're gonna have head, and you're gonna have tail. Okay, so what I have now, this is actually, the sample space for the experiment in a situation where a random variable x actually follow binomial distribution with a sample size of 3. The numbers of trial equal to 3, and the probability probability of the characteristics of interest. The characteristics of interest here now is basically the number of X. Okay, the number of X that we're going to show up is a characteristics of interest. Okay, so when you have this guy now, so um what you basically going to have, give me 1 second, I'm actually gonna clean up now. So if I set up my probability table, which I call the PML, of course, I've walked you through that. You know what I mean? I've walked you through the PML. So if I want to set it up now, so all what I'm just gonna do, I'm actually gonna have X, and I'm gonna have uh, a lowercase f of X, then 0, 1, 2. Okay, then I'm gonna have 3. Okay, now X, don't forget, X is actually the numbers of X, right? Okay, so X can go from 0 to 3. Okay, when you take a look at this now, that is a situation where the numbers of X equal to 0, and that is going to be 1 out of 8. If you look at the cardinality of the sample space, right, you basically have 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. That's what I mean. Okay, so how many times do we have one head? Okay, you're also gonna look at that. I think this guy here. Oh, sorry. Oh, sorry about that. That's not one head. That's two head. Okay, so this is one head. One. Okay, so two, 3. So that's going to be 3/8. Take a look at that. Then how many times do we actually have her head? Okay, where we have that is going to be 1/8. Okay, and if how many times are you going to have two heads? So basically that is going to be 3/8. So take a look at that. So that's a PMF. Okay, that's a probability mass function. But you know what? If you want to get the CDF now, you need to for set up your probability mass function. So this guy here is actually the PMF. What I set up in that table now is PMF. Okay, so if I want to write that out, okay, what I'm gonna, if you take a look at the lowest values of X here is 0, right? Okay, the lowest values of X is actually 0. We don't want a situation where S is going to be a negative. You get what I mean, right? And that is the reason when you want to figure out the CDF now, you're basically going to say the CDF, an uppercase f of S, will basically be equal to 0 for X less than 0. Yeah, you get what I mean, right? And for X lie between 0 and 1, is going to be 1/8, as you can see. Okay, as you can see here, S lies between 0 and 1. It means S greater or equal to 0, but X less than 1, that will be 1/8. I want you to take note of that. And you know what, between 1 and 2, okay, between 1 and 2, you more or less like trying to say, when S is greater or equal to 1, so you have 1/2. Okay, and how do you get 1/2? If you add, we're going to be cumulating, right? Okay, so what is 1/8 plus 3/8? That's going to be 4/8, which is going to be half. That was how you got this guy now. Okay, so when you add 1/2 next to 3/8, okay, you're basically going to have 7/8, which is what you have here. Okay, when you now add 7/8 to 1/8, okay, 7/8 to 1/8, that is going to give you 1. And that was how you have this. And that is basically going to be for 3 less or equal to X, or X greater or equal to 3. Now, before you can actually get your CDF, you need to first get your PMF. Okay, we've gotten our PMF. Now we got the CDF now. So what I'm trying to talk about now, this guy is actually the distribution function, okay, for this particular distribution. And you know what, you can only talk about the quantile if you already have your distribution function. I'm going to say that again. You can only talk about quantile now. You can derive your quantile, now that you have your distribution function. So what I'm trying to tell the world now is before you can actually figure out your, what quantile is from a particular probability distribution, you need to first, figure out what is your the PMF, and that is what I actually have. So now from there, now that I can actually make an inference about what the quantile is going to be. So as you can see now, we're actually using this guy now. Okay, 0 is a unique Q quantile for Q lie between 0 and 1/8, and X is a 1/8 quantile for X lie between 0 and 1, and 1 is a unique Q quantile for Q lie between 1/8 and 1/2. Okay, we actually talking about this guy here, this guy here. That is exactly what we're actually using now. Okay, and of course X is 1/2 quantile of the X lie between 1 and 2, and so on like that. So I just want to take note, okay, about. But there's something I just walk you through the quantile for discrete random variable now, using the probability mass function, binomial distribution. But what if in a situation, so how do we figure out the quantile from continuous probability distribution? For example, we actually want to talk about an exponential distribution. Okay, if X is an exponential distribution random variable, then how can we actually find the Q quantile? I'm going to say, we need to for derive the CDF, or the distribution function of exponential distribution. I'm going to stop my share now, so that, I told you, if you basically want to, if you want to derive the quantile of any probability distribution, you need to first actually get a CDF of that particular distribution. So I'm going to share my whiteboard now. We're talking about a random variable X, that follow exponential distribution with parameter lambda. So what is the f of x? The f of x is basically lambda exponential is power minus lambda x, where s is greater than 0. Okay, so I need to forget the CDF of this. I need to get the distribution function of this particular distribution before I can actually figure out what the quantile is. Okay, so if I want to get a CDF, that is an uppercase f of x, okay, which is the probability of x less or equal to small x. I'm actually gonna go from 0 to x. Don't forget, if you want to find a CDF, it's actually gonna terminate at a particular point s. Okay, then I'm gonna write lowercase f of t dt. Okay, so if I want to rewrite that now, I'm gonna write 0 to x. What is f of t? I'm gonna write lambda exponential is power lambda t dt. You're actually going to change t to x. I mean, you're going to change s to t, because we actually the upper bound is actually x, it's terminating at x. So in the this distribution, we're not going to use x variable. I just wanted to take note of that, but that doesn't change anything. Now if I integrate this guy now, so what am I actually gonna get? So this is gonna be lambda exponential is power minus lambda t divided by minus lambda, from 0 to x. Okay, now lambda cancel lambda, and I'm actually gonna have minus exponential is power minus lambda t, then 0 to x. Okay, so I'm actually gonna plug in x and 0 now. Okay, plug in that. So I'm actually gonna have minus lambda x, okay, minus exponential is power that of 0. Okay, so what am I going to have? The minus and minus is going to be a plus, and exponential carrying 0 is going to be 1. So I'm actually going to have this guy now. Okay, minus is going to be a plus, and exponential is power 0, so which is 1. So finally, I'm actually going to have 1 minus that. Take a look at this. So what I'm trying to tell you now, okay, that is a distribution function of exponential distribution. Okay, don't forget, what I actually want to get is the distribution function, right? I want to get a quantile function of exponential distribution, but the very first thing I actually need to do is to first get the distribution function. I told you the other time the uh, prerequisite to get the quantile function is to first figure out what the distribution function of that particular distribution is. Okay, so I started with an exponential distribution. And of course, I stated the probability density function of the exponential distribution. Then from there, I derive, the distribution function, which is 1 minus exponential raised to the power minus lambda s. And after that, now, what I'm basically going to do, I want to figure out, the quantile. So, if I want to find the quantile, you know what I'm going to do. Don't forget the other time I told you when you're talking about continuous random variable, we're basically going to equate the distribution function to the equal to q. Okay, so to the equal to q, and we're basically going to solve for x. Okay, then let me just I'm gonna write that. Then solve, okay, for s. Okay, now you're going to see what I'm actually going to do now. So what did I derive as a distribution function? Actually derive distribution function, the f of s for exponential is basically 1 minus exponential is power minus lambda s. I'm actually going to equate that to q. When I equate that to q, then I'm actually going to solve for x. Okay, when I solve for x, okay, that is basically going to be the quantile. The quantile is actually an inverse of the CD of the distribution function. I'm going to say that again. Quantile, okay, is the inverse of the distribution function. So what I'm trying to say is that what I'm going to do now, I'm going to solve for x now. So this is going to be minus exponential raised by that equal q minus 1. Okay, if I multiply both sides by minus, of course, I'm actually going to have this guy equal to 1 minus q, right? And minus lambda x, it will be ln, okay, log of exponential. Okay, the log of exponential 1 minus q. So if you divide both sides by minus lambda now, because I'm looking for x, I'm actually going to have, minus 1 over lambda, the log of exponential 1 minus q. So take a look at this now. Okay, this is a quantile function. Okay, so this is a quantile function now. Okay, for exponential distribution, you saw the way I derived that. To get a quantile function, to put a quantile function in place, what I needed to do is to first, derive the distribution function of that particular distribution, for continuous random variable. Then I'm going to equate that to q. Then I'm going to solve for x. And you know what? The q that you have here now that we call, if you want to find the median, let's say I ask you to find the median of exponential distribution, you're going to plug in half for q. Okay, I can actually find, what about, finding the lower quartile. The lower quartile is basically 1 over 4. Okay, and the upper quartile is 3 over 4. All what you just need to do is to plug in that into that. So which means if you have a continuous probability distribution and you are asked to find the median, okay, when q equal to half, that is going to be the median. For this time, you want to find the median of of a exponential distribution. Now, okay, you're basically gonna plug in q. Okay, the moment you know your lambda, the lambda is actually the parameter of the distribution. So the moment the lambda is known, you can actually use this to figure out what the median is, what the lower quartile is, and what the upper quartile is. Okay, I don't know whether you've heard about that. You have what we call the lower quartile. Okay, we have the upper quartile, right? Okay, I don't know whether you've heard about that before. And I said, if you want to get a lower quartile, you're going to plug in q to be 1 over 4 into the expression the moment you know your lambda. And for the upper quartile, you're basically going to plug in q to be 3 over 4. And if you want to find the median, okay, let's say what you want to find is a median, you're going to plug in Q to be equal to half. Okay, so that is the essence. I just wanted to take note of what I've just explained. Now, you remember the other time I said if I want to guarantee that 95% of my customers get their order within 24 hours, what would be the numbers of inventories I'm actually going to have? So if you take a look at that very queue now, okay, if you decide to plug in the 0.95, okay, if you plug in the 0.95, you know, you can determine what your S is going to be. For instance, if your distribution, if the distribution of the ordering, the way they order your product, if it follows exponential distribution, that is when you can use this expression for that. Okay, I'm going to stop my share now. And of course, I'm going to go back, to the material. Okay, I think I've just shown you how to do, how it is. Okay, this is the solution, the x equal to -1 over lambda. Okay, the log, that very log is actually the natural log, okay, of 1 minus q. And of course, this is the quantile now. This is the quantile function of exponential distribution. And of course, I told you what they can use a quantile, okay, to figure out. We can use a quantile to find the median, the lower quartile, the upper quartile, and so on like that. Okay, all what you just need to do is to plug in, the appropriate value for Q. When Q equal to 1 over 4, you have the lower quartile. When Q equal to 1 over 2, you have the median. When Q equal to 3 over 4, you have the upper quartile. Of course, you can actually determine that when you're actually given lambda. Don't forget the lambda is a parameter of an exponential distribution. Okay, I think I just mentioned all this now. So the 1 over 2, the 1 over 4, the 3 over 4, the 1 over 2 is a median. That is the values you're actually going to plug in for Q if you want to figure out what a median is. And 1 over 4 is what you're going to plug in for Q if you want to figure out how the lower quartile, and 3 over 4 is what you're going to plug in for Q when you want to talk about the upper quartile that I just actually talk about. And if it is a percentile, you want to use, but of course, instead of that, like if you want to talk about the 90 percentile, of course, you basically going to plug in 0.9. If you want to talk about 75 percentile, you can plug in 0.75. You want to talk about whatever percentage, of course, you're actually going to plug in that, to replace Q. And of course, you'll be able to determine what your corresponding value of X is. Okay, so I think I just mentioned that, I've walked you through how to get a quantile function. And the only way you can get quantile function is where you actually, when a random variable S has a distribution function, I told you the other time. Okay, so I think I've been able to walk you through the quantile function of exponential distribution. Don't forget, I for derive the distribution function from the given exponential distribution. Then I saw for x, and from there I was able to, derive the quantile function. And of course, don't forget the quantile function actually lies between 0 and 1. Okay, we're not going to have 0 quantile, we're not going to have 100%. Quantile is basically going to lie between, it's going to be greater than 0 but less than 1. Okay, and I gave you the example on the binomial distribution the other time, like how to get a quantile for a discrete random variable. I think I demonstrated that. So what I'm just going to tell you, when you have a distribution, you need to first figure out what the distribution function is going to be, because the only way you can get a quantile of a function is for you to first obtain a distribution function, which I actually call an uppercase F. So I think I demonstrated this to you the other time. Okay, and if you based on this now, I got this guy from the PMF. Okay, where I demonstrated to you the other time when I was actually using coin. Okay, I first set up the sample space, Then from the sample space, I actually, set up the PMF, the probability mass function, and I was only accumulating to get the CDF right here. And of course, based on what you have, we can get a corresponding quantile function for that. So when you want to talk about the quantile function, because this numbers of trial is 3 for binomial, you're actually going to go from 0, 1, 2 to 3. And of course, you're actually going to tell the word, okay, for 0, Q lie between 0 and that. For 1, it lie between that and that. And for 2, it lie between that and that. And for 3, it lie between 7/8. Of course, it's very, very easy if you want to know that, okay. When you take a look at this now, you're going to see between 0 and 1/8. That is when you have for s equal to 0, okay. And of course, between 1/8 and 1/2, okay, what do you actually have is 1. Less or equal to 1, so that's what you have, okay. And between 1/2 and 7/8, okay, between 1/2 and 7/8, okay, what you have is actually 2, okay. And of course, between 7/8 and 1, then what you have is actually 3, okay. So this is the quantile of this corresponding distribution function. Okay, so what the takeaway from the quantile is just that if the support of a random variable is a whole real line, okay, it's talking about all numbers a real number, then the distribution function is invertible, okay, and the quantile function is its inverse. I think I told you the other time, okay, the quantile function is inverse of distribution function, okay, which means it is only when the distribution function is invertible that you can actually figure out, okay, the quantile function, which happen to be the inverse, okay. So I just want you to take note, of that. And of course, we have, I demonstrated to you the example of quantile function, okay. Number one is cited example from a discrete probability distribution. I use binomial, and from there, I also walk you through the exponential distribution, which is one of the probability, one of the probability distribution of a continuous type. Okay, do you know in a normal distribution, okay, every probability distribution have a distribution function, and the moment you have it, they have a distribution function, and it's the inverse of them. We actually we exist, and we can figure out with the quantile function, okay. The distribution function for normal distribution, we normally use this guy. So the inverse of that is going to be a quantile. Okay, you can say that this guy is the inverse of that. If this guy here, phi, is a symbolic, a representation, a notation for the distribution function of a standard normal distribution, then the inverse of that is basically going to be a quantile. And I also want to say for other probability distribution, we can also figure out the quantile function. Only that there are some distributions that we may not be able to explicitly derive. The function may, the quantile function may be complex, but I want to say they can actually be derived. Okay, so I just wanted to take note of that. We just talk about the. I think the next, objective of the day is what we call the best prediction. Some of you in statistical theory, before we actually observe, okay, we normally have a certain values in mind of what, since our mind can not be empty, in statistics, there are situations where we use the mean as a guess, and we also got situation where we use the median, okay, particularly in time series where we do forecasting. A lot of people will be wondering is the average, forecasting prefer to the median forecasting, stuff like that. So I'm going to tell you the best, the prediction, whether to use the mean or to use the median. I think it actually depends on, the kinds of, measure that we adopt. I'm going to say that again. Using the mean as a best prediction or median as a prediction depends on the criteria, okay, that we're actually using. Okay, if we basically want to minimize the expected square error. Okay, if you want to minimize the expected square error, of course, if you find the mean and you find the median, okay, the mean we actually minimize that. Okay, the median is not able to minimize that. I'm going to say that again. I said, whether to choose between mean or median. Okay, whether to choose between mean and median, uh, as a prediction, as the best guess, as the best prediction, that actually depends on the criteria you are using. If you are actually want to, because anytime, whenever you have a guess, there's always going to be a loss function that we want to minimize. Okay, that the different kind of loss function that we have could be, the expected square error, the absolute error. Okay, so if the criteria we're actually using is the expected square error, okay, the mean, the expected value of S that we call mean is the best guess. It's going to be the best prediction. Okay, but if you actually if the criteria you want to use is the absolute error loss, of course, is you actually going to use the median, because when the mean and the median was used in that regard, the median actually minimize the absolute error loss, better than the mean. And when it comes to expected square error loss, the mean actually did a very great job compared to median. And of course, that's what we're trying to say here, where the mean is what we call the expected value of X. Like I said, is the best prediction when we basically want to minimize this. Of course, when you differentiate this guy here, okay, when you differentiate this guy here, of course, you basically going to say the optimal value you're going to have is actually going to be the expected value of X. Okay, so what we use the mean as the best guess. If the criteria to minimize is expected square error. Okay, I just wanted to take note of that. But we could have situation in statistical analysis where mean does not exist. Not only that mean does not exist, maybe using the mean in statistical analysis, it is requires that the probability distribution of the data set should be normal. Okay, situation where the probability distribution of the data set is not normal, or situation where there's an outlier in a data set. You know what I mean by outlier? According to Camp in 1982, outlier is a data point that is not consistent with the rest. I'm going to say that again. We have a data point that is not consistent with the rest. If you want to find mean in that kind of situation, you could mislead. Okay, you could mislead. In that situation, it is not going to be appropriate to use mean as a best prediction. And of course, we could use, median in that situation. Okay, median is robust. Median is robust, to outlier. Okay, I just wanted to take note of that. Okay, so this is the mean absolute error that I talk about. That's okay. We actually use this criteria when, the best guess, the best prediction is median. Okay, and I think I've just demonstrated to you now when you can actually use median. Okay, number one, when mean don't exist, or the probability distribution of the set of random variable is non-normal, and not only that, maybe there's an outlier in the data set. Of course, using the mean will not be appropriate. We actually going to use you're going to use median. And you know what, when you're using median, of course, the criteria is basically that you want to minimize is actually mean absolute error. Okay, so the mean absolute error of prediction is actually minimized when A is any median of the distribution of X. And of course, I told you how you can get the median of a distribution. Okay, if you have a continuous probability distribution, we need to first obtain your quantile function. And how are you going to get your quantile function? I think I told you, you basically going to derive your distribution function, then you equate that to Q, then you solve for X. When you solve for X, you basically have your quantile function in place. Or what you're just going to do, where you see Q, you're just going to plug in half. Okay, when you plug in half, then you have your median. Okay, and of course the median, how to tell how reliable is the median. Okay, you can actually obtain the mean absolute error. Okay, because the median is expected to minimize. The mean absolute error of prediction is expected to be minimized. Okay, when you actually consider median. Okay, I think I demonstrated that to you now. Okay, I want to actually walk you through some derivations now. Our situation, where suppose M is a median of X. Some of you in a lower case or lower level statistics course, when you're given set of observation, you want to find the median. Of course, after sorting them in ascending order or in descending order, the middle value is actually median. You get what I mean, right? And if you want to find the mean, it's just adding up all the observations together and divide by the number of the observation. I think you understand that. Okay, now I want to walk you through something now. Suppose M is a median of X. Okay, and if M actually lies between X and A, I just wanted to see this now. We say M is the median of X. And if M lie between X and A, okay, don't forget here, M is greater than X, but M is less or equal to A. Okay, now the absolute value of X minus A minus the absolute value of X minus M, okay, we can rewrite that as this. Take a look at this now. Okay, if I want to remove the absolute value, I'm just going to switch. That's exactly what I'm doing here. If I want to remove the absolute value, I'm actually going to switch X for M. That's exactly what I have here. And this is going to be minus M plus X. That's plus S is cancelled out. I'm going to end up with A minus M. Take a look at that. Okay, now, I just consider a situation. You remember the other time when I was walking you through different kind of intervals? The intervals that we use here actually lead us to this. You get what I mean? Okay, the intervals that we actually use here, okay, actually lead us to that. Okay, what if in a situation where I'm actually using this interval now, where it includes M and A. Take a look at that. Okay, take a look at that. Okay, now if I rewrite this guy again here, okay, now that I'm talking about different kind of interval, okay, I'm still I'm gonna switch this guy here. You have this, but you are not going to switch this. Okay, I just wanted to see the difference. The other time, okay, right here when I'm considering this, I have to switch to remove the absolute value. I have to switch X for A, X for M. That gave me this. You get that? But now that I'm actually considering this the interval now, okay, I'm only going to switch this. Okay, when I'm removing that, okay, I'm not going to switch this guy here when I'm removing the absolute value, and that's what you see here. So here now, you have a minus X plus M. Take a look at that. So automatically, I'm actually going to have a minus 2x plus m. So which is this guy here? Now that is when I use that interval. Okay. Now, what if I use this interval? Right now, it's like actually switch that interval for that. You see what I got? Okay. Now, what is going to happen? When that happen, I'm not going to, when I want to remove the absolute value here, I'm not going to switch anything. I'm just going to do that. Take a look at that now. Okay. So you can see I have x minus a. I did not switch this as well. I wanted to take note of that. Okay, why am I not switching now? Because of the fact that, you know, uh, I'm using a different interval now. A is in the middle. Okay, I'm not going to switch this. That's why I have this. I'm not going to switch this. Uh, you know, After removing the absolute value, I'm not going to switch that. Then by the time I simplify now, okay, minus x plus m, take a look at that. So this is going to cancel that, and automatically that will give me minus m plus m, okay, which is more or less going to be minus into a minus m, which is what I have here. Now I get three possible scenarios. Now take a look at that. So these are the three possible scenarios. And what am I going to do to them? What I'm going to do to them is just to tell the world I'm going to distribute that. Okay, so summarizing that now. Okay, situation where I'm considering it, I'm actually going to write all of that, all the three scenarios, and I'm actually going to tell the world, okay, situation under which each of them is actually applicable. For this is x minus that, for that is this, and for that is that. So take a look at that now. So you basically, when I get a minus m, okay, the other time, you basically gonna see here that that occur at x less than m. Okay, so at x less than m, that's what you see here. At x less than m, that give me a minus m. Okay, okay, I just want to see that. Look at that. S less than n is giving me this. Okay, and at this, okay, at this interval, that's what I have. So that was why I wrote this guy here. Take a look at that. And if you look at the last one, it's basically going to be at s greater than a, because take a look at this. When a is less than s, that implies s is greater than a. That is what it means. Okay, and that this is what I got. Okay, and that was why I put that here. You see that now? Okay, s greater than a. That's what I got. Okay, now when I have this guy now, so what I'm gonna do, so this guy now would be, since all this, it can be this, when this can be that, when that, okay, then I can actually say, okay, this guy now, okay, is greater or equal if I use this guy, okay, and two into and this guy here, okay, and two into that. So I'm going to say it's basically greater or equal to that with an indicator. Okay, I just want to take note of that. Some of you may be wondering, what am I trying to do? Well, what am I driving at? I'm actually driving at the absolute error. I'm actually going to the absolute error. Okay, so using the idea here, if I introduce expectation now, okay, expectation, introducing that now, I'm actually going to have that. Okay, and when I introduce expectation now, don't forget, what I'm just trying to do, introducing expectation here, we got this, introducing expectation here, we got this, introducing expectation on I. Don't you remember the other time, we've already figured out how expected value of I is actually probability associated. You understand what I mean? You remember sometime I've been able to, when I was trying to say expectation is a special form of probability is a special form of expectation. Do you remember that? I think we're recalling that now. Okay, so that was how the expected value of I, that is the probability. Don't forget. Why is it probability? I think you remember when I was walking you through, because that indicator is it's binary. You get what I mean? Okay, I think I derived that before. So take a look at that. Okay, so in the end, you basically gonna see that the whole of that will be greater or equal to zero, which is what I have right here. Okay, I just wanted to take note of that. And when you have this guy, whatever A may be, okay, now in summary, I'm gonna say, if you take a look at this guy now that we call the expected absolute error, okay, the median is actually the best prediction. Okay, the median is actually the best prediction. Okay, and we actually use that if the first moment don't exist, like so if the first moment, because the first moment is actually the mean situation where it doesn't exist, of course, I think I told you, you know, whether it doesn't exist or is not appropriate, like when you have some set of data and you have an outlier, or the probability distribution of the data set is not normal. Okay, you can mean it's not going to be you know, is not going to be a best prediction for that. And what is going to be the best prediction is basically going to be median. Okay, I think that is actually the takeaway. Okay, the mean is the best prediction. Okay, if you're minimizing expected square error, but median is the best prediction if you're minimizing absolute error. Okay, and what else? And sometimes, okay, what would be the best prediction if some other criteria were used? So which means what is going to be the best prediction, what you can consider best prediction depends on the criteria and the situation of your data set. Okay, I'm going to hide that. I'm going to say that again. What would be the best prediction between mean and median? Okay, between mean, okay, mean and median, what would be the best prediction between mean and median? All depends on the nature of the data set and the criteria you are using. I think I just demonstrated to you. Mean is actually the best prediction if you're trying to minimize the expected square error, and the median is going to be the best prediction when you are minimizing the expected absolute error. And of course, if you're using other criteria, okay, the mean and the median may not be the best prediction. Okay, so which means the whether mean or median is going to be the best prediction actually depends on the criteria you are actually using. Okay, so this is where I'm actually going to stop today. Like I said, my laptop actually crashed initially, but that has been restored now. I'm actually going to return back to the live lecture tomorrow. Like I said, this particular lecture will be shared with you on the course canvas. So make sure you stay safe and have a lovely day. So bye for now, everyone.